Hello my dear students, today I am going to give you some shortcuts in solving questions based on molecular orbital theory. We know for NEET and JEE from chemical bonding and molecular structure, the most important topics are hybridization and molecular orbital theory. Okay, these are almost equally important for competitive examinations, all competitive examinations. You see every year in NEET examination, minimum 3 to 4 questions are coming from this particular unit. So molecular orbital theory is also very important topic from this unit. So generally questions, which type of questions come from molecular orbital theory? You will be given some diatomic molecule or ion, then you have to find out the bond order, or you have to compare bond energy or bond stability, okay, magnetic behavior, I mean diamagnetism, paramagnetism, like that. So for that, how to solve this numerical? In our syllabus we have homonuclear diatomic molecules, generally up to 20 electrons we have in our syllabus. You may be asked some heteroatomic molecules also. There is no problem for homoatomic and heteroatomic. You are not going to face any problem. So our first task is, when you are given any molecule like this diatomic molecule or ion, first you have to calculate total number of electrons. We know in H2 2 electrons, He2 4 electrons, like this up to atomic number 10, that is neon 2 molecule. If it exists, just let us see. Okay, so 20 electrons are there. So this is the energy order, increasing energy order of various molecular orbitals. Okay, from sigma 1s to sigma star 2pz, this is the increasing energy order. But before solving molecular orbital theory based question, you have to understand that up to 14 number of electrons, one type of configuration, that is 2s 2p mixing, is operative. So that's why sigma 2pz is placed away from sigma star 2s. Because of small energy difference, they may mix, they may overlap with each other. Already one question came in JEE Advanced related to this concept. If 2s 2p mixing is not operative, then what would be the magnetic behavior of C2? Okay, like that. That model question came. C2 or B2, or that molecule was given. So up to 14 number of electrons, 2s 2p mixing is quite operative. Post 14 electrons, 2s 2p mixing is not operative. So the order of molecular orbitals is quite different up to 14 electrons and beyond 14 electrons. So this one you have to notice carefully before solving any question. So first you have to count the total number of electrons and which kind of configuration you have to write, either this one or that one. Okay, then only you start solving the question. So well, in H2 we have only 2 electrons. You see, an orbital can accommodate maximum 2 electrons. He2 4 electrons are there. So you see the configuration, sigma 1s2, sigma 1s2, sigma star 1s2. So like this, when electron number increases, you can progressively fill up orbitals by respective number of electrons. 10 electrons are there. But you see carefully, in NCERT we are also mentioned that we have to follow Aufbau principle, Pauli's exclusion principle, and Hund's rule. So you have to follow Hund's rule as well. So B2 is paramagnetic, because we know if unpaired electron is there, that should be paramagnetic. So C2 is there, total 12 electrons are there. So strictly Hund's rule we have to follow in filling molecular orbitals, just like atomic orbitals. Okay, like this, 14 electrons are there. Up to this 2s 2p mixing is operative. Okay, so after this 2s 2p mixing is not operative, or we can also say that up to 2s sigma star 2s sigma 2pz electrons are filled. In both the orbitals, electrons are filled. Okay, so there is no problem. That's why post 14 electrons, up to 14 electrons, the difference is clear. So here again, you see 16 electrons are there. In the same way, you can fill up all the electrons. Actually, this diagrammatic representation gives you a simple shortcut, means all molecules in single page. You can take screenshot of this one, so you can understand total molecules along with bond orders also. And F2 we have total 18 electrons we can fill as per Aufbau principle, I mean increasing order of energies of various orbitals. Okay, and finally we have neon. 20 electrons are there. You see this one. Okay, so up to 14 electrons, the configuration is like this. After sigma star 2s, pi 2p, this is actually pi 2px and pi 2py. There is no space, that's why I didn't mention here, but I mentioned here. You see, pi 2px, pi 2py, they have same energy. Degenerate orbitals. That's why here we have to strictly follow Hund's rule. Pi star 2px, pi star 2py, these are anti-bonding molecular orbitals. Already you know very well, wherever sigma pi are there, sigma pi, okay, these are BMOs, sigma star, pi star represent ABMOs, anti-bonding molecular orbitals. Asterisk is clearly mentioned for anti-bonding molecular orbitals. So this is total diagram for atomic number 1 to 10, all molecules in single page. Now how to calculate bond order? I want to calculate bond order. Bond order formula you know very well, half into number of electrons in BMO minus number of electrons in ABMO. This is the formula of bond order. So how to calculate bond order? So first you see number of electrons in BMO, that is 2. Number of electrons in ABMO, number of electrons in ABMO, that is 0. No electron is there. So half into 2 minus 0. So 1 is coming for hydrogen. So this is the actual way of finding bond order. So for any molecule you can calculate bond order like this. Okay, so first you take a screenshot and you can calculate bond orders as well for every molecular species. Like this, you see hydrogen, for hydrogen half into in BMO 2 electrons are there, ABMO no electron, the bond order is coming 1. So if hydrogen molecule is present, then between hydrogen and hydrogen single bond is present. And look at this, BMO 2 electrons, ABMO 2 electrons, the difference comes to be 0. So when difference is 0, half into 0 again 0, it is 0 in case of He2, He2 0, H2 1. Okay, what about this Li2? Li2, what is the bond order? 2 plus 2, 4 electrons in BMO and 2 electrons in ABMO. So 4 minus 2, it comes out to be 4 minus 2 into half. So again bond order is coming 1. And in BMO 4 electrons, ABMO 4 electrons, the difference is 0. So in case of beryllium 2 molecule, bond order is coming 0. And 1, 2, again you see 2 more electrons are there. This is BMO, pi 2p, sigma 2p, these are BMOs, these are ABMOs. Okay? So now you see clear that overall 2 plus 2 plus 2, 6 are there. 6 are there in BMO and 4 are there in ABMO, and half you are getting 1 bond order. B2 is exceptional case. Paramagnetic, that is presence of unpaired electron. In B2 single bond is there. As per our earlier knowledge, we all know that if a single bond is present between two atoms, that should be sigma bond. But in B2 and C2, these are exceptions in which the single bond present in B2 is clearly, that is no doubt, pi bond. It is not sigma bond because these electrons are present in pi molecular orbitals. So bond is formed between these two electrons and these are present in pi molecular orbital. So that's why in B2, although single bond is present, that should be pi bond. One of the exceptions. Already in sigma and pi bond differences, I taught this point in clearly. I mean, very few compounds, in very few cases, pi bond is formed without formation of sigma bond. In general, after formation of sigma bond, pi bond formation takes place. But in these two examples, B2 and C2, only pi bonds are there, not sigma bonds. Even for C2, it is mentioned in NCERT as well. The bond order is 2 because 2 plus 2 plus 4, 8. 8 minus 4, 4 by 2 is 2. like this. N2 you can calculate, because once you know how to calculate BMO minus ABMO upon 2 in the same formula, you can apply. For O2 bond order is coming 2, and for F2 bond order comes out to be 1. For neon 2 bond order comes out to be 0, because we know that noble gases in elemental state, I mean in atomic state, they behave as molecules, so they are already stable. So that's why 0 bond order means there is no bond formation between 2 heliums, 2 beryllium, 2 neon, like this. Means their diatomic molecules do not exist. Only already in monoatomic state they are stable. Noble gases, you see, neon, helium, already they are stable in monoatomic state. Their diatomic molecules are not stable. 0 bond order means that molecule or ion does not exist. Bond order increases. When bond order increases, bond strength increases, stability also increases. Okay, so bond order is 1. Bond order is 0, this molecule does not exist. Bond order is again 1, again 0, it does not exist. 1, 2, 3, it means bond enthalpy increases. Bond becomes more and more strong. That's why you see N2 bond order is 3. N2 reactions at room temperature are very rare. Whatever the reactions we talk about N2, they take place at relatively higher temperatures because of presence of triple bond between 2 nitrogen atoms, and very high energy is required to break this triple bond. So with increase of bond order, bond strength increases, stability of that molecule increases, and O2 again a paramagnetic species. You see, 2 unpaired electrons are there, paramagnetic. B2 is paramagnetic, remaining all are almost diamagnetic. Unpaired electron, paramagnetic. No unpaired electron, diamagnetic. So by using this you can solve how many model questions? First you can calculate bond order. After that you can judge which molecule exists, which does not exist. Third one, you can identify the magnetic behavior, whether it is diamagnetic or paramagnetic. Okay, so these are general model questions from this, and you may be asked like this: which is more stable, which is less stable? So for that you have to compare bond order. Higher the bond order, higher the stability of that species. So you are given ions. Okay, suppose you are given ions like this one. Here I am writing because already this is over now. Because in some NEET and JEE examinations also some questions came like N2, N2 plus, N2 minus, O2, O2 plus, O2 minus. So that kind of questions, when we are given that kind of questions, O2 you are given O2 plus 2, O2 minus, O2 minus 2, like this. Nitrogen N2 plus, N2 minus. You are asked to find stability of these species. Actually, in molecular orbital theory, there is a trick we know. Addition of electrons to BMO or removal of electrons from ABMO increases the bond order. And simultaneously, removal of electrons from BMO and addition of electrons to ABMO decreases the bond order. Because bond order formula we know very well. Number of electrons in BMO minus number of electrons in ABMO. When I add electron to this, then bond order increases, because this value increases means bond order increases. So when I remove electron from this value decreases means bond order increases. So in reverse case, when I remove electron from this or add electron to this, bond order decreases. So that's why stability again decreases. So it is a simple trick. When you add electron to BMO, then bond order increases. When you remove electron from BMO, bond order decreases. Similarly this one, addition to this, bond order decreases, removal from this, bond order increases. So if you know O2, already we know that in O2 final configuration, I mean pi star 2px, pi star 2py, one electron is there, and bond order is 2, you know, bond order of O2 is 2. Now I want to talk about O2 plus. O2 plus is formed by removal of electron. So from where we should remove electron? From this from final molecular orbitals. So anyway, either from 2px1 or 2py1 you remove electron, and this is removal of electron from ABMO. When you remove electron from ABMO, bond order increases, we know, but up to what extent? You see the formula, before this half is there. When you remove one electron, then half value increases, 2.5. 2 electrons I want to remove these 2 electrons. You remove 2 from ABMO from this. Okay, so value of n ABMO is 2 units less, then into half means 1 value increases. It becomes 3. It means you have to understand that when we add electron to BMO, an electron, single electron to BMO, or remove single electron from ABMO, bond order changes by half, that increases by half, and vice versa. Now O2 minus means I have to add electron. Here vacancy is there, yes, add one electron here, and I have added one electron in ABMO. When I add electron to ABMO, the bond order must decrease, no doubt. Addition of electron in this. So before this negative sign is there, so bond order decreases, but for what extent? Half extent. 2 minus half, 1.5. So one more electron you add here. So because of addition of 2 electrons in comparison to O2, so bond order decreases by 1. So bond order is coming 1. Okay, so you can easily understand that which has highest bond order, O2 plus 2 has the highest bond order, so that must have highest stability, and O2 minus 2 must have least stability, because stability is always directly proportional to bond order. So highest bond order, highest stability, least bond order, least stability. So this model questions also coming in competitive examinations, and suppose you are given any question in which bond order is same. Suppose bond order is same, then how to solve that question, sir? Generally you said that with increase of bond order, stability increases. Suppose bond order is same. Okay, let me solve that question also. Li2 you have Li2 plus Li2 minus. Li2 means how many electrons are there? 6 electrons are there. 5 electrons are there. 7 electrons are there. 6 electrons means you know the configuration. Sigma star 1s2. This is also called K star, because first we know in an atom very first orbit that is actually nearest to the nucleus, that is called K shell. So that's 1s is present in K shell, we know. So K shell is completely filled, means K star we can write. Okay, so sigma 1s2, sigma star 1s2, and after that sigma 2s2. So what is the bond order in lithium? 2, 4 minus 2. We have already calculated 1. Now you see, I am talking about lithium plus 5 electrons, means sigma 1 is 2, sigma star 1 is 2, sigma 2s1. So total 5 electrons are there. What is the bond order now? Half into 3 minus 2, that is coming 0.5. That is coming 0.5. 1 by 2, 0.5, and 7 electrons are there. Sigma star 2s1. What is the bond order now? Half into 4 minus 3. 4 BMO, 3 ABMO. 1 by 2, that is 0.5. Sir, actually lithium 2 is more stable, no doubt, because in lithium 2 one bond order is there. So lithium 2 should be the highest stable. Between Li plus 2, this is Li2 plus, this is Li2 plus, this is Li2 minus. Both have same bond order. They should have same stability? No. Okay, already it is clearly written in NCERT that more the number of electrons in ABMO, that destabilizes the system. So if more number of electrons are there in ABMO, okay, then that decreases the stability. Here actually only 2 electrons are there in ABMO. One additional electron is there in ABMO. 2 plus 1, 3 electrons are there in ABMO. More number of electrons in ABMO decreases the stability. So it is clear that Li2 plus is more stable than Li2 minus. Okay, so there are two model questions, that is clear. On the basis of bond order, if bond order is same, then you see number of electrons in BMO and ABMO. If you are given heteroatomic molecule, then also you can calculate. There is no problem. In the same way, in the same energy order, you can calculate. Suppose you are given carbon monoxide. Carbon monoxide 14 electrons. If you know nitrogen, then you can directly answer this. Nitrogen also has 14 electrons. In N2, triple bond is there. Between carbon and oxygen also triple bond may be present. So like this, in general we write like this. Okay, this is actually day 2 bond. We know carbon cannot form three bonds along with lone pair. So generally triple bond is present. Just like N2, in CO also triple bond is there. But here one exception is there. So there is a standard exception. When CO is converted into CO plus, I mean when electron is lost, 14 electrons are converted into 13 electrons. We already know that in N2, that is there here, in N2, okay, final electron is there in BMO. And the 13 electrons are there. So this one is formed by loss of electron, we know. And this electron should be removed from BMO. If we remove electron from BMO, then bond order in general decreases. We know in general, in all cases. The only exception is CO plus. In CO plus, after formation of CO plus, that extra electron is present here between carbon and oxygen. Okay, so because of this, because of presence of this electron in between carbon and oxygen, bond order changes from 3.3 to 3.5. I mean 3 bonds are already there. This extra electron is present between carbon and oxygen, that is located here, that is also considered as half bond. So in this exceptional case, carbon monoxide to CO plus, bond order increases. In all remaining cases, when you remove electron from BMO like CO and N2, bond order always decreases. Okay, so this is about almost complete information regarding molecular orbital theory and very important for competitive examinations. Thank you.